Hi, welcome to physics. This is Mrs. Dalberg, and today we're talking about acceleration and how do you know when you're accelerating? Um, so we know that we have acceleration going on when you speed up, when you slow down, or one more thing, when you turn, when you change directions, you also accelerate. And so all of those have to do with changing your velocity. And so if you write a word equation for acceleration, we know that acceleration is the change in velocity over the change in time. So if we change our speed by speeding up or slowing down, we change our velocity. But we can keep the same speed, but if we change direction, since velocity is vector, it has magnitude and direction, we also change the acceleration. In symbol form, that would be A equals delta V over delta T. Now the symbol for acceleration is A, and the units are interesting. If we look at velocity, the units of velocity are meters per second, and time, if it's in seconds, we end up with meters per second, or meters per second squared. And if you think about it, it's kind of weird to have a second squared, but what does that mean? It just means that for every 1 second, we're changing our speed by 1 meter per second. And so that's where the square comes from. Now, if we look at this kind of takes you through describing acceleration, kind of like you did with Mad Libs back when you were a kid. So a car's acceleration is 5 meters per second squared. That means the car's speed or velocity increased by 5 meters per second every second of time. And so that's what that's saying when we say an acceleration is 5 meters per second squared. This is a common one that you would probably see more in everyday life. Accelerations with units like these. So if you see a car commercial and it says it goes from 0 to 60 miles per hour in 2 seconds, what does that mean? It means the car's speed increases by 60 miles per hour every 2 seconds time. Um, so that means the car's acceleration is 60 miles per hour every 2 seconds, or 30 miles per hour per second. The acceleration of a falling object is 10 meters per second squared. If a penny is dropped from the top of the Empire State Building, let's fill this in to find out what happens. So the penny's speed increases by 10 meters per second every second of time. And so every second that goes by, the speed increases by 10 meters per second. So if we had to compare velocity and acceleration by using the word rate of change to write a sentence about them, we know that velocity is the rate of change of position, whereas acceleration is the rate of change of velocity. So in other words, acceleration is the rate of change of velocity, which is the rate of change of position. So it's the rate of change of the rate of change of position. So that's kind of interesting. So now let's talk about what would a graph of motion look like for these types of motions. And today we're going to throw in not only our position and velocity graphs that we've been doing, but also acceleration graphs. And if we look at the first one, if we look at a position time graph of something standing still, we have something standing in a position, and the position originally doesn't matter. I'm going to say this person starts right here and is standing still. So this kind of graph would be a horizontal line. Now, if we're trying to find velocity from the position graph, we know that the slope of this graph gives us the velocity. So in other words, to go from here to here, we need the slope. And so if I look at this, it has a slope of 0 the whole time. Now, if we look at velocity, if the velocity is not changing, not moving at all, then the acceleration is going to be 0 as well. He's not changing his speed. But what you may not know is that if we want to get acceleration, we can get it from the velocity graph. And the way we would do that is to take the slope. And that will give us our acceleration. So let's look at this one. Moving forward at a constant velocity. Kind of review that. So if we're moving forward at a constant velocity, we start at some position. We can start at 0, but we don't have to. We could start right here. But our graph would look the same. We would have a straight line with a slope. Now the slope of this line gives us the velocity, and this slope is constant and positive, so we have a constant positive velocity. And if we have a constant positive velocity, if our velocity is constant, that means it's not changing, so our acceleration is 0. Now, if we are moving backward at a constant velocity, we start away from 0 and move back. And so if we look at that, what would that be? That would be a constant negative velocity. We have a constant negative slope, so that tells us we have a constant negative velocity. And so our velocity graph would look something like this. And if we have a constant velocity, we have no acceleration. Okay. Moving on, we are going to talk now about speeding up and slowing down. And so these first two we're moving in the positive direction. And if we're speeding up in the positive direction, our graph of motion would start maybe at 0. We don't necessarily have to start at 0, but we would have something where we have a changing speed. And in this kind of graph, you would start to see a curve whenever you're speeding up. Now, if we look at the velocity graph for this, let's kind of figure out what would our velocity look like. If you're speeding up, you're going from slow to fast. And if we look at the slope of our line, we're going to draw some tangent lines and find the slope at various points. If we look at the beginning, our slope is 0. And then it increases to a more positive number, like 1. And then it increases even more to a more positive number like 2. And so that means our velocity is changing from something like 0 to 1 or 2 or to a more positive number. So our velocity graph would start at 0 and increase. Now, if we have this going on, the slope of this graph gives us our acceleration. And if you look, we have a changing velocity. So we definitely have an acceleration. And the slope of this graph is positive and constant. So we have a positive constant acceleration. Okay, slowing down in the positive direction. So again, we're going to start here and we're going to end up over there. We're going to start at 0 and move away. But now we're slowing down. And that would mean my position is not changing as much as I keep going. And so if I start here, this graph would look something like that. And so if I take my slope meter and I draw a tangent line at various points on this graph, and I figure out the slope of my tangent line, I have some positive number. The slope is pretty steep right there, and it's getting less steep and eventually going to 0. And so this is what's going on with my velocity as I'm slowing down. So I would start maybe at some positive number and go toward 0. Now, if I look at this, slowing down in the positive direction, if I have a velocity graph, and this should be a straight line, I realize it looks a little curved, but that's not intentional. The slope of this is negative and constant, and so my acceleration is negative and constant. Okay, for the next two graphs, we're going to be speeding up in the negative direction. And so what does that look like? Now, if we're headed in the negative direction, we're going to start away from 0 and head towards 0. And if we're speeding up, that means our position is going to change more and more as we go through time. And so this is speeding up in the negative direction. And if we look at that, the slope of this graph tells us how our velocity is changing. And so if we draw tangent lines at various points, we can see that our slope goes from something like 0 to 1 to 2. It gets more steep, but not just more steep, it also is negative. And so if we look at that, what would that translate to on the velocity graph? Well, this means that he has a velocity of 0, a velocity of -1, and a velocity of -2. If you're headed in the negative direction, your velocity graph will be in the negative quadrant. And so it would look like that. Now, here's something interesting. If you have this graph, the slope of this graph tells you the acceleration. And the slope of this graph is negative and constant, so I have a negative constant acceleration. So for our last graph, we're slowing down in the negative direction. So again, if we're going in the negative direction, we're going to start our position graph here and head to here. But slowing down means that we are not going to change position as much as time goes on. And so this graph looks like that. And so if we draw our tangent lines to figure out what's happening to our velocity, we get things like that going on. And so if we look at how our slope is changing, we have at the end, we have a slope of essentially 0. Right here, we have a slope of maybe like 1, and it gets steeper, so it's 2, but those slopes are negative. And so we can't forget those negatives. And so what we have going on for our velocity graph is we have a velocity of something like -2 going to 0. So if you're in the negative direction, your velocity graph will always be this negative quadrant. Now, if we look at this graph, the slope of this is positive and constant, which tells us I have a positive constant acceleration. Okay, so look at those graphs we just made and see if you can come up with some rules about when velocity is positive or acceleration is positive. If you can notice a few patterns in these graphs that we just made, this will go a little bit easier for you. Thanks, and I'll see you later. Bye.